In this session, I would like to continue with conditional probability. So we'll do a few examples of probability and conditional probability using the ideas that we've built up in the previous sessions. Okay, so first example. Supposing that 20% of LUMS applicants are accepted, 50% of accepted students get hostile accommodation. What is the probability of being accepted and getting hostile accommodation? Okay, so using this information, we want to start by labeling events and putting down the information that we've been given in terms of these events. So let A be the event that an applicant is accepted, and let H be the event that a successful applicant has been given hostile accommodation. Okay, so then we were given that the probability up here, 20% of LUMS applicants are accepted. So that's the probability of A is 20% or 0.2. 50% of accepted students get the hostile accommodation, right? So let's be a little bit careful with that. That's the probability that a person is given hostile accommodation given that they have been accepted. That's 0.5. Okay. Now, what did we want? We wanted the probability of being accepted and getting hostile accommodation. That's an intersection of A and H. So the multiplicative rule says the probability of A and H, the probability of the intersection between A and H, is the probability of A times the probability of H given A. And we were given these two. The first one is 0.2, the next one is 0.5, giving a result of 0.1. Now, let's take a look at the next one. Flip a fair coin 3 times, the probability of getting 3 H's in a row, 3 heads in a row. Okay, let's think about that for a second. How many outcomes are there? Well, the first flip gives you a head or a tail. The next flip gives you a head or a tail. The third flip gives you a head or a tail. And if the experiment is recording these 3 results in order, then you have 2 times 2 times 2 is 8 possible outcomes. It's a fair coin, so all of these outcomes are equally likely. And then the result is one result meets is the one that one outcome is the one that we want out of 8 equally likely outcomes. So the probability of 3 heads in a row is 1/8. Okay. Now, again, we're going to flip a fair coin 3 times. We're going to record the results in order. There are 8 equally likely outcomes. What's the probability of observing exactly 1 head in 3 flips? Well, how can you get that? You can get that as HTT, THT, and TTH. So 3 outcomes out of 8 equally likely outcomes meet our requirement. So from the work that we did before, the probability of that requirement being met is 3 out of 8. Okay. Another way of looking at it is you have 3 outcomes, 3 events. So one event is getting THH, the other event is getting HTH, and the other event is getting HHT. So if you're asked, what's the probability of observing, say, okay, I think I've interchanged head and tail. But anyway, the probability of observing exactly one tail is the same as the probability of observing exactly one head. The probability of THH union HTH union HHT. Remember, we had that formula where you have to subtract out probabilities of intersections. But these events are mutually exclusive. So the intersections are empty. The probability of the intersection is 0. So we can just add up the probabilities of the individual events. And each one is 1 out of 8. Probability of each one of these events is 1 out of 8. They're equally likely. So you're going to get 3 out of 8. Okay. An example. Next example. Probability of at least one H. Probability of at least 2 H's. Okay. So, well, let's look at all the equally likely outcomes. How many? There are 8 equally likely outcomes. How many of them have at least one H? Well, 7 out of 8, I think. At least 2 H's. Okay. Think about that for a second. So let A be the event of at least 2 H's. Let B be the event of at least 1 H. If we're given, if we want something like the probability that you have at least 2 H's, given that you have the probability of at least 1 H, that's the probability of, that's by definition, the probability of A intersection B divided by the probability of B. Now let's think about this intersection for a second. A is at least 2 H's, B is at least 1 H. So A is a subset of B. So A intersection B when A is a subset of B is just A. Okay, so that's probability of A divided by the probability of B. It's 4 out of 8 divided by 7 out of 8 is equal to 4 out of 7. Next example. You have 2 blue socks and 3 red socks in a drawer. So you take out one sock at random, right? You close your eyes, you just put your hand and feel a sock and take it out. Then the second time, and you don't put it back, right? And then the second time you reach in, close your eyes, pick up one sock at random and take it out. Okay. What's the probability of 3 red socks being left? Okay, let's think about that. In order to have 3 red socks left, what I have to have done in both, I started with 3 red socks. So if I took any red socks out, then I can't have 3 left. So that means that this is the same as, what's the probability that both times I drew 2 blue socks? Okay. Well, okay, so let B1 be that the first sock drawn is blue. B2 is that the second sock drawn is blue. We want the probability of both these events occurring. So B1 intersection B2. So B1, probability of B1 intersection B2 by the multiplicative rule and our definition of conditional probability. That's the probability of B1 times the probability of B2 given B1. Now the probability of B1, the first sock drawn is blue. Okay, you had 2 blue socks and 3 red socks, so you had 5 red socks in a drawer. You had 5 total socks in the drawer. The probability of getting one of the 2 blue socks out of the 5 socks is 2 out of 5. Now, the probability of drawing a blue sock, the probability of drawing a blue sock the second time, given that you drew a blue sock the first time, so you had given B1. So that means if B1 is certain, that means you had 2 blue socks and 3 red socks. And then you took out a blue sock. So now you've got 1 blue sock and 3 red socks. So the probability now of the second time drawing a blue sock would be 1 out of 4. Okay, so probability of B1 is 2/5, and the probability of B2 given B1 is 1/4. And so the multiplication rule, the multiplication gives us 2/5 times 1/4 is equal to 2 out of 20, or 1 out of 10. Okay. Think about this one a little bit. Same setup. You have 2 blue socks, 3 red socks in a drawer. You take one out blindly without replacing it. You take out another one at random blindly without replacing it. What's the probability that you have 2 red socks left in the drawer? Okay. Well, that's the probability that you took out. In order to have 2 left, you have to remove exactly 1. So either you took out a red sock followed by a blue sock, or you took out a blue sock followed by a red sock. Okay. So let A be the event that you took out a red sock followed by a blue sock. Let B be the event that you took out a blue sock followed by a red sock. Now, what's the probability of A? A is red, then blue. Well, you had 3 socks out of 5 were red, so you had 3 out of 5. And then the next time, you had 4 socks left, and 2 of them, you had 2 to choose from, were red. Were blue, so that's 2 out of 4. 3/5 times 2/4. And I'll let you think about the second one. That's 2/5 times 3/4. So the probability of one or the other happening, A union B, A or B. Okay, that's the probability of A plus the probability of B minus the probability of A intersection B. But A intersection B is empty, right? If A is occurring, B can't occur. If B is occurring, A can't occur. That's probability of A plus probability of B. We add the 2 probabilities that we found, and then we got 6 out of 10. Okay. Still not tired of the sock example. 2 blue socks, 3 red socks in a bag. You take 1 sock out without replacing it. You take another one out without replacing it. What's the possibility of 1 red sock being left? Okay, that probability is that, how could that happen? You'd have to take out a red sock, and then the next time you'd have to take out a red sock, leaving you with 1 red sock. Okay, I'll leave you with that one. You should get 3/10. Okay, get away from the socks for a bit. So you got 6 prisoners in a dungeon. Let's label them 1, 2, 3, 4, 5, 6. One of them is to be released at random. Okay, as an act of mercy. Okay, now the way we're going to release it, we're going to do this is like this. We're going to have 5 white marbles and 1 black marble in a bag. So prisoner 1 will take out 1 marble without replacement. And if they draw the black marble, then prisoner 1 goes free. If prisoner 1 isn't lucky, prisoner 1 will not return these marbles that we drawn without replacement. So now you've got 4 white marbles and 1 black marble in the bag, and prisoner 2 is supposed to draw. If prisoner 2 draws the black marble, prisoner 2 is released and the selection process stops. If prisoner 2 does not get the black marble, that means now that there are 1 less white marbles in the bag, and there's 1 black marble in the bag, and so on and so forth. First prisoner to draw the black marble is released. Now, in order for this to be fair, each prisoner has to have the same probability of being released. Each prisoner has to have the same probability of drawing the black marble. Okay? So to decide if the process is fair, we need to work out the probability. What probability is it that each prisoner is released? So let's think about this. For the first prisoner, what's the probability? Well, you're drawing, there's 1 marble, there's 6 total marbles, 1 of them is black. They're drawn at random, each one is equally likely to be drawn. So the probability of prisoner 1 being released is 1/6. Okay. What's the probability that prisoner 2 goes free instead? Okay. Well, so let's think about this. Prisoner 1 is unlucky with a probability of 5/6. There are 5 marbles left, 4 white, 1 black. The probability of not drawing the black is 1/5. So what needs to happen? You need to have it's a 2-step process now, right? So prisoner 1 has to be unlucky with probability 5/6 for prisoner 2 to even have a chance, and then prisoner 2 has to get lucky. Okay, so then the result would be 5/6 times 1/5, which is 1/6. So prisoner 1 and prisoner 2 all have the same, both have 1/6 probability of being released. And if we run the same analysis for everyone, we would get 1 out of 6. Okay. All right, so finally we come to a somewhat more serious question of probability, conditional probabilities, and that is how you interpret medical tests. And the strange thing is that doctors routinely misinterpret these tests. When they're given a result, they routinely overestimate the likelihood that the patient has the disease or the condition that's being tested for. So this one is important. Okay. Conditional probability in medical tests. Okay. So there's a test which indicates that you have a rare disease. Okay. What's the probability that you actually have that disease? Sometimes the tests are wrong. Okay. So what's the probability that you actually have this? Okay. So there's a bit of terminology that we need to know. We talk about false positive, false negative, true positive, true negative. Okay. So tests sometimes give false positives, right? It's an indication that the disease is present when it is not. So when the test says that you have the disease, but you don't have the disease, the test is said to have given a false positive. Okay. Tests can also unfortunately give false negatives. So a negative result means that the test says that you don't have the disease. So you can get a false negative, and that is the test indicates that you don't have the disease when in fact you unfortunately do have the disease. Okay, so that result is called a false negative, right? And you might be given that the probability of a false positive or probability of a false negative with this test is some probability. Okay, so false negatives, we discussed that. Okay, now there's the false positive rate. This is the fraction of healthy individuals who will be incorrectly given a positive result. So that means, you know, if the false positive rate is 1%, that means out of 100 people who are healthy, one person will be given one person will be given the false news that they in fact have the disease, even though they're healthy. And that's the false positive rate. Similarly, false negative rate means that you know, if let's say for every 100 people who actually have the disease, 2 of them will be told that they don't have the disease. Let's say, then the false negative rate would be 2%. Okay, so let's say we have Doofenshmirtz syndrome. It's a terrible rare disease, and well, I don't know if 1% is rare. Anyway, 1% of the population is believed to have Doofenshmirtz syndrome, for which there is a test. Okay. Now, the false negative rate is 20%. That means that out of 100 people who actually do have DS, 20 of them will be told that they don't have it when they actually do have it. We're given a false negative rate. Okay, false positive rate. The false positive rate is 10%. That means that out of 100 people who don't have the disease, DS, 10 of them will be told that they actually do have it, even though they don't have it. 10% false positive rate. Okay, so making a table might help us to see this. Okay, so here, this row has DS, doesn't have DS, test positive, test negative in the columns. So the people who don't have DS, 10% of them will be given something wrong. Okay, and for people who do have DS, 20% of them will be given the wrong information by the test. Okay. Now we can work out the rest of the table. If 20% of the people with DS are told that they don't have it, then 80% of the people are told that they do have it. Okay, so you can fill this. You can fill in one of these, and then for the remaining one, if 10% of the healthy people are told they are unhealthy, then 90% of healthy people are told that they are healthy. Okay, so we can fill it in like this. Note that the rows should be summing to 100%. Okay. Now you put in some numbers. Let's say we were dealing with 1,000 people. So 1% of 1,000 people is 10, right? So we believe that 1% of the population has the disease. So if we picked 1,000 people from the general population randomly, 1% of them, that is 10 people, should have this disease. How many of them won't have the disease? That's 990. Okay, so out of 1,000 people, 10 will have the disease, and 990 will not have the disease. And we can work out 8% of that and 20% of that, 10% of 990, 90% of 990. Okay, so 80% of the 10 who have DS is 8, 20% of the 10 who have DS is 2. So we could put 8 and 2 in brackets there. 10% of the 990 who don't have DS is 99, so we could put 99 in this box. And 90% of the 990 who don't have DS is 891. We could put 891 in that box. So you can fill that in. You know, you don't have to make the table if you don't want to. I find that it helps. There's several things going on that I need to keep straight in my mind, so it's nice to make a table sometimes. Okay, now let's sum the entries. So yeah, it was 1,000 people. There's 107 will test positive. Whether that test is accurate or inaccurate, and 893 will test negative. Does that add up to 1,000? Yes, it does. And so now, let's say the T means that the test says that you have DS. So the test is saying that you have DS. And D is the event that you actually do have DS. Okay. So now we would like to know is, what is the probability that the person has DS, given that the test says that they have DS? Okay. What is the probability that any general person has the disease? That was 1%. Now, what if the test says that the person has the disease? What is the probability that the person has the disease, given that the test says that they have the disease? Okay. So that's our conditional probability. That's the probability that the person has the disease, given that the test has the disease. That's equal to the probability that the person has the disease and the test says that they have the disease, divided by the probability that the person has the disease, divided by the probability that the test says that they have the disease. The probability of D given T is the probability of D intersection T divided by the probability of T. Now, if we go back to our table, what's the probability that the test says that they have the disease? Well, we tested 1,000 people, 107 of them will be told that they have the disease. So that's 107 over 1,000. That's 0.107. Okay. Okay. What's the probability that a person has? What's the probability the person has the disease and the test says that they have the disease? So they have the disease and the test says that they have the disease. That's 8 people out of 1,000 fall into that set, that intersection. They both have the disease and the test says that they have the disease. That's this here, 8 out of 1,000. Okay. So probability of D intersection T is 8 out of 1,000. the probability of T we said was 107 out of 1,000. So the thousands cancel, that's 8 out of 107, and that's 0.0748. Okay. All right, so the probability that any random person has the disease is like 1%. If you also give me the information that the person tested positive for the disease, then that's about 7.5% that they actually have the disease. Okay. And if that required a major intervention, maybe you should get a second opinion. Okay. So ending on one serious application of that, and that concludes our discussion of examples, material that we've done before.